So we are back, and in this topic, we will focus on using ProcessFRS as a safety platform in order to implement some protections and limited control on a compressor. So consider we are on offshore in a remote area, and we want to run a system, a compressor, a machine, and we want to do the safety parts, oil circuit, surge control, temperature control of different part of the machine, surge control, the pressure, dynamic behavior in pressure response, and also vibration and some limited control. So ProcessFRS has the capability for complex programming, but the main concept of using ProcessFRS is to implement safety logics in plants that somehow fire and gas is an issue. Safety, ESD, emergency shutdown systems are important. So in gas plants, oil plants, and petrochemical plants, ProcessFRS will play or is playing a vital role in ensuring safety of those plants. But we had several other examples: fire and gas, emergency shutdown, and burn management system. And in this course, we cover all of them. But the last project is somehow a complex project. We want to show you that the ProcessFRS has the capability to perform some controls when it's needed, limited control. Unlike Siemens doesn't have the all-leg output in safety, but it has a standard and fail-safe structure in the same controller. But in ProcessFRS and other safety manufacturers, safety PLC manufacturers, you have the option of using all-leg output in the safety PLC. So if you are in a remote area, so you need some limited controls, even PID control, a safety PLC should be able to do that. The safety logic should be very limited, very small safety logic, but you don't want to make another cabinet for the control part. You can do all of them in the same solution. So this is the oil circuit and the rest of the protection of control of a machine. But the whole program is developed. We are interested in a start blocking feature in this machine. Let me move to the ProcessFRS. So we are in the ProcessFRS environment. The program is developed in several languages. The basic programming language is function block diagram FVD. It has some powerful tools to implement some other blocks, like you can write your own complex functionalities by using a structured text. These are all functions that are developed by a structured text to do the complex tasks. So let's see if possible to, from tools, I need to fetch maintenance and start the test function here. So I created the program. I did simple function test. by simulation, and this is the final result. It can be improved and some parts can be changed. This is a normal procedure. Normally, when you have the control philosophy, you implement your program in a test environment, and if everything is successful, you move all of those thoughts on hardware, perform similar function test before installation on an actual machine or plant. So we need to wait to have the simulation ready, the Centum VP environment. And in that environment, you can visualize the plant, the machine, and interact with the safety, send commands, and show indications. So some buttons are connected to the machine. We don't have the feature of testing actual buttons here, so the machine. So some parts are protection parts, and some of those are control parts. So let us this is a stop button, and let me release the emergency stop. I need to press acknowledge in order to return to normal state. So we are in normal state, so we don't have those push buttons, so I need to make them on and off again. So acknowledge is off here. I press permission, so we need to wait 30 seconds to evaluate the permission. During the permission, some actuators are running. The oil will be pumped by the electrical auxiliary oil pump to the oil circuit, and this is the mist remover. So there is a control philosophy explain how to run these actuators, so we don't waste our time to dig into how these are operating. So now I can start. So after the 30-second permission, I can start the machine here. So let me perform a start here. So you can see that the main drive is starting, and normally in the oil circuit, after the main drive is working and the mechanical oil pump is able to drive the oil pressure here, we are happy with the oil pressure and turn it off. There's some option to turn on the oil pump, auxiliary oil pump again based on this pressure. If this pressure is dropping some levels, we can turn this oil pump on in order to compensate the oil pressure. So the set point for pressure is 8K, 8 bar, and now we are closing the this BOV. You can see that 4075, and this input is getting open. This part is somehow related to the control part, the control part that is implemented in the ProSafeRS. As I mentioned, ProSafeRS is not intended to perform some control applications, but it has the tools for you to write your own PID application if you need some limited controls. in a remote area, but the main purpose of using ProSFRS is only for a safety reason. So the pressure set point is 5 bar. We need to wait until reaching to the 8 bar, and after reaching to 8 bar, the inlet guide vane should reach to the steady state. After that, it's possible for us to increase the set value and check the result. In here you can see that the oil pump is getting off, auxiliary oil pump is getting off here. So all of these values are available in the ProSFRS dictionary. You can go online and check all of those values, change those values, and see what's the actual behavior. So so set value is getting to 7K. I want to show you the actual values as an example. Some unlock values. These are the unlock values. You have the option to change these values and see the response here. So I will revisit this project again and again. We check the control philosophy, function test, everything again. In this example, we simply want to reach to the set value, and the PID controller that we used here. Let me show you the PID controller. It's PID generic. It's a PID generic developed by myself, and we used Riemann for integration calculation, and Euler method or Rank-Kutta for differentiation, calculating the differentiation. So this is the PID algorithm that can be used even in any other PLCs. It's a simple calculation block, and all of these blocks, like rate of change limiter, and all of those blocks are developed in a structured text. So we are getting to 8K. Let me increase the set value to like the set value. I changed the set value to 12K. So you can see that we have a more opening on the input. That we decrease the set value to 70. So still pressure is increasing here, and we will reach to the set value. This is the just introduction. If we want to test the blocking, the startup blocking, that will be our next function test. The temperature in the internal temperature of the drive is checked if the drive is running in hot or coldest, warm or cold conditions, and there is a limit for number of startups in warm or cold. That will be our next function test. I will do that in the next function test. So we are getting the pressure will be increased here. If you want to generate a shutdown, simply now we can press a stop in order to shut down the whole machine. Another cool feature that we have in the ProSFRS is the first trip out functionality. in process that it will report if you have several trip signals at the same time. It will inform you what was the actual first trip out in those lists on the long list of trips signals. So when we stop the machine, we need to pass a stop phase. During the stop phase, these two drives should continue pump. The oil pump should continue pumping oil to the machine, and when this is pumping, the oil mist also should running in order to extract the mist out of the oil tank. So a sub phase is finished, and everything is off, standstill. I stop the video here, and in the next video we will function test the several unsuccessful startups, and the safety PLC should block the machine for 1 hour, block starting the machine for 1 hour. So I stop the video here, and we do the function test for the next video.